There is a star in our sky that appears to be older than the universe. Not slightly older. The universe is approximately 13.8 billion years old. Methuselah, officially catalogued as HD 1400283, has been measured at roughly 14.46 billion years. That would make the star hundreds of millions of years older than the universe that supposedly created it. And this is not some distant object nobody can study. Methuselah is only about 190 light years away, close enough that it can be found with binoculars. It is moving through the Milky Way at roughly 800,000 miles per hour, following a long orbit through the galaxy's ancient outer regions. Its chemistry makes the mystery even deeper. Methuselah contains remarkably little iron, along with very low amounts of carbon and oxygen. Its composition suggests that it formed when the universe contained far fewer heavy elements than it does today, potentially placing its birth among the earliest generations of stars. But that creates the contradiction. If the universe is 13.8 billion years old, how could anything inside it have existed for 14.46 billion years? Astronomers have been confronting that problem for decades. Improved measurements have reduced the uncertainty, but the age paradox has remained one of the most fascinating problems surrounding this seemingly ordinary star. Maybe the original age estimate is wrong. Maybe something about the star's history has been misunderstood. Or maybe the tension is pointing towards something deeper about the age and evolution of the universe itself. This channel grows because of people who take a moment to like and subscribe. If you're one of them, thank you. It means we get to keep doing this. Let's talk about what we actually know. A star's age is hidden inside its structure, encoded in the slow changes taking place beneath its surface. We cannot read a birth date from starlight. We reconstruct one from the physics of stellar evolution. The most useful map for this is the Hertzsprung-Russell diagram, which places stars according to their brightness and surface temperature. As a star changes, it moves across this diagram in recognizable stages. Hydrogen burns in the core, fuel decreases, the interior contracts, the outer layers respond, and eventually the star leaves the stable phase that defined most of its life. That sequence gives astronomers a clock. For Methuselah, also catalogued as HD 1400283, the important clue is its position as a subgiant. It has nearly consumed the hydrogen available in its core and has begun transitioning toward a larger, more evolved state. This phase is comparatively brief, making its position especially useful for estimating how much time has already passed. Mass provides another part of the calculation. More massive stars burn their fuel rapidly and live relatively short lives, while smaller stars consume hydrogen much more slowly. Methuselah belongs to the long-lived class, but its composition makes the calculation more revealing. Stars are rarely made from only hydrogen and helium. Elements heavier than helium are collectively called metals in stellar astronomy, even though many of them are not metals in the everyday sense. Their abundance changes how energy moves through a star and influences the rate at which its interior evolves. Methuselah contains extraordinarily little iron. Its iron abundance is roughly 250 times lower than the Sun's. That scarcity points toward an ancient birth environment, one that existed before repeated generations of massive stars had enriched surrounding gas with heavier elements. To estimate its age, astronomers combine several observations. They measure the star's brightness, determine its temperature, analyze its chemical composition, and establish its distance. Those measurements are then compared against computer models that calculate how stars with different masses and compositions should evolve over time. The calculation becomes a search for the model that best matches the star we actually observe. But every input carries uncertainty. A tiny change in the assumed composition can alter the predicted rate of nuclear burning. A subtle difference in temperature changes the star's position on the evolutionary diagram. Even the amount of helium hidden within its interior matters, because helium influences how quickly the available hydrogen is consumed. We therefore do not obtain an age by reading one perfect number from one perfect instrument. We build an age from several pieces of evidence, each carrying its own uncertainty. For most stars, those uncertainties remain comfortably smaller than the timescale being measured. Methuselah is different. Its properties place the calculation close to the oldest possible age allowed by cosmology, so details that might seem minor become enormously important. The star's age is therefore less like a timestamp and more like the endpoint of a long chain of physical measurements. Every link matters because when the final number reaches billions of years, even a small shift in the underlying physics can change the entire story. The first clue was motion. Against the fixed pattern of distant stars, HD 140283 seemed to drift noticeably from year to year. Early photographic surveys recorded that movement long before anyone suspected the star carried a cosmological problem. Its proper motion, the apparent change in position across the sky, is about 1.45 arcseconds each year. That made it one of the fastest moving stars known from our neighborhood. Astronomers followed it as a high velocity halo star, tracing its unusual path through the Milky Way. For decades, nothing about its age demanded extraordinary attention. Then stellar models improved, and the numbers began behaving strangely. Around the year 2000, updated calculations produced an estimated age of roughly 16 billion years. The result exceeded the accepted age of the universe by a substantial margin. That immediately suggested something closer to home was wrong. Distance was the obvious suspect. A small error in a star's distance changes its calculated luminosity, and luminosity changes the evolutionary track used to estimate age. If the distance were wrong, the entire calculation could shift. So astronomers went after the distance itself. Howard Bond and his colleagues at the Space Telescope Science Institute used the Hubble Space Telescope's fine guidance sensors to measure Methuselah's parallax. Parallax is the tiny apparent shift produced as Earth moves around the Sun, allowing the star's distance to be determined geometrically rather than inferred from brightness. The observations were collected across 11 separate epochs. Each measurement added another point to the star's apparent motion, allowing the team to isolate an extraordinarily small shift against the background sky. The resulting distance was about 190.1 light years, with an uncertainty of less than 1%. That was the measurement the age calculation had been waiting for. When Bond's team placed that distance into the stellar models, the age fell dramatically from the earlier 16 billion year estimate. But it did not fall far enough. The published central estimate was 14.46 billion years, with an uncertainty of roughly 800 million years. Its lower boundary reached about 13.66 billion years, barely beneath the accepted cosmic age. The central value remained older. That distinction matters. An uncertainty range tells us where the true value could reasonably lie, while the central estimate represents the model's most likely result. Methuselah's range overlapped the universe's age, yet its preferred value still crossed the boundary. Bond did not hide that tension inside technical language. The paper directly acknowledged the conflict between the stellar age and cosmological measurements, then examined several possible sources of error. For us, the remarkable part is what happened next. The distance measurement had become far more precise, yet the contradiction survived. The problem was no longer an obvious mistake in the star's location. It had moved deeper into the assumptions used to turn stellar light and composition into a measurement of time. The contradiction becomes clearer when we place Methuselah inside the timeline of cosmic history. A star needs matter, gravity, and enough cooling for that matter to collapse. Before those conditions existed, there was simply nowhere for a star to be born. During the universe's earliest stages, everything was compressed into an intensely hot plasma. Protons, neutrons, and electrons moved through a radiation filled environment where stable atoms could not yet survive. For roughly 380,000 years, the cosmos remained in that state. Eventually, expansion cooled the universe enough for electrons to settle around atomic nuclei. Light could travel freely, yet stars still did not exist. Gravity needed additional time to gather the thin hydrogen and helium left behind after the primordial expansion. The first stellar generation, known as Population 3, probably appeared roughly 100 to 200 million years after the beginning. Their formation establishes an important boundary for Methuselah. Even under an extremely early scenario, a normal star cannot predate the material and conditions required to make it. That leaves Methuselah's central age estimate of 14.46 billion years in direct conflict with the cosmic timeline. If that estimate were literally correct, its birth would fall hundreds of millions of years before the universe could have produced stars at all. So, what could be wrong? We have three broad possibilities. The stellar age could be overestimated because some ingredient in the evolutionary models remains imperfect. The cosmic age could be underestimated because our description of the universe's expansion is incomplete, or both measurements could be slightly displaced in opposite directions. The cosmic clock comes from the cosmic microwave background, the faint radiation released when the early universe became transparent. The Planck spacecraft mapped that radiation with extraordinary precision, allowing cosmologists to reconstruct the universe's composition, expansion, history, and age. Its best estimate places the universe at about 13.8 billion years old. The uncertainty is remarkably small compared with the timescale itself. Yet another measurement of cosmic expansion produces a different result. Astronomers studying nearby galaxies and stellar distance indicators consistently infer a faster expansion rate than the value derived from the early universe. This disagreement is called the Hubble Tension, and it has resisted increasingly precise observations. A faster expansion rate generally corresponds to a younger cosmic age. That direction only makes Methuselah's problem harder for us. The important distinction is between a logical impossibility and a measurement that exposes a weakness in our assumptions. Methuselah does not prove that the universe is older. It shows that two powerful clocks, built from very different physics, are not fitting together as neatly as expected. The star's existence therefore reaches beyond stellar astronomy. Its age estimate touches the timeline of the entire cosmos, forcing us to compare what happens inside one ancient star with what the universe itself says about when everything began. Methuselah's spectrum carries a history written in the arrangement of its atoms. When starlight is separated into its component colors, narrow absorption features appear where specific elements have removed particular wavelengths. We can read those features as chemical fingerprints, revealing what entered the star's birth cloud billions of years ago. The striking feature is scarcity. Iron is roughly 250 times less abundant than in the Sun, while carbon is extremely deficient. Oxygen is also sparse overall, yet its abundance relative to iron is unusually high. That combination gives astronomers something more useful than a simple measure of age. It identifies the kind of stellar debris from which Methuselah formed. Hydrogen and helium were produced in the early universe, but most heavier elements required stellar furnaces. Iron, carbon, and oxygen emerged through nuclear reactions inside earlier stars and were later dispersed when those stars ended their lives. Each generation, therefore, changed the chemical material available to the next. Methuselah contains remarkably little of that accumulated enrichment. Its iron abundance corresponds to a metallicity of roughly negative 2.4 on the logarithmic scale astronomers use to compare stellar compositions. In practical terms, its iron content is about 1/250th of the Sun's. That scarcity places Methuselah among the ultra-metal poor stars, a rare population whose chemistry preserves conditions from the earliest chapters of the Milky Way. Yet, the oxygen pattern adds another layer. Oxygen is enhanced relative to iron, suggesting that the gas forming Methuselah was influenced by massive stars whose lives were brief and whose explosions produced particular mixtures of elements. Those ancestral stars belonged to population 3, the first generation of stars. We have never observed one directly. Their lives were probably measured in millions of years, and some may have reached hundreds of times the Sun's mass. Their enormous interiors forged elements that the universe had previously possessed only in tiny amounts. When these giants died, their material spread into surrounding gas. A later cloud could then collapse into new stars, carrying traces of those earlier explosions. Methuselah appears to be one of those descendants. Its atmosphere preserves a chemical mixture that formed after very little stellar enrichment had occurred, giving us a rare glimpse of a transitional universe where the first elements heavier than helium were beginning to circulate. You can think of its chemistry as a record of sequence. Hydrogen and helium came first. Massive stars followed. Their deaths altered the raw material, and Methuselah emerged from what remained. The remarkable part is how little history separates those stages inside this star. Its atmosphere has been preserved for billions of years, allowing modern spectroscopy to recover information from an era no telescope can observe directly. We are seeing the aftermath of stars that disappeared before the Milky Way had settled into its present form, preserved in one ancient survivor. A star's path through space can preserve the circumstances of its birth long after its birthplace has disappeared. Methuselah's motion gives us exactly that kind of evidence, revealing a history written across the enormous architecture of the Milky Way. The Sun follows the galaxy's rotation, traveling around the central regions within the broad stellar disk. Methuselah takes a very different route. Its orbit carries it far above and below that disk, reaching into the extended halo before curving back toward the inner galaxy. Astronomers call this a halo orbit. It is characteristic of stars that formed during the Milky Way's earliest stages, before the galaxy had developed the organized disk we see today. The halo surrounds the Milky Way like a vast, diffuse population of ancient stars and globular clusters. Its members move on varied paths, many of them tilted sharply relative to the galactic plane. Their motions preserve traces of a time when the galaxy was still assembling from smaller systems. Methuselah's particular trajectory is especially revealing. It is traveling through our region of the galaxy at roughly 800,000 miles per hour, a remarkable speed that reflects its elongated orbit and its gravitational history. We happen to encounter it during one passage through the neighborhood. That encounter is temporary. Over immense spans of time, Methuselah rises away from the galactic disk and travels outward toward the halo. Its path then bends under the Milky Way's gravity, eventually bringing it back through the inner regions. One complete journey takes far longer than any human civilization has existed. The orbit also gives astronomers clues about where the star may have formed. One possibility is that Methuselah originated in the outer regions of the young Milky Way, where early stellar populations could survive before the galaxy's structure became more settled. Another possibility reaches beyond the original boundaries of our galaxy. The early Milky Way grew partly through mergers with smaller galaxies and fragments of primordial systems. Stars belonging to those smaller galaxies could have been captured by the Milky Way's gravity, becoming permanent members of its halo while retaining distinctive trajectories and chemical signatures. If Methuselah arrived through such an ancient merger, its present location would be the result of a journey lasting billions of years. The small galaxy that once contained it could have been dismantled completely, its stars scattered across the halo, while Methuselah continued along its original gravitational path. You can think of the orbit as a surviving trace of that vanished structure. We cannot travel backward and watch the Milky Way assemble itself, but stellar motions allow us to reconstruct pieces of that history from the present. Methuselah's route therefore tells us something its surface alone cannot. Its chemistry records the material from which it formed, while its orbit records the environment that carried it across the galaxy. The star is passing through our part of the Milky Way only for a brief moment in its immense journey. Beyond this region, its elongated path continues, carrying an ancient survivor back toward the outer halo where the galaxy's earliest history remains preserved. There is another clock running beneath the age of Methuselah, and it belongs to the universe itself. Cosmologists call its central measure the Hubble constant, a number describing how quickly space expands across enormous distances. One way to estimate it begins with the oldest light we can observe. The Planck spacecraft measured patterns in the cosmic microwave background and used them to test a detailed model of the young universe. That model gives a Hubble constant of about 42 miles per second for every megaparsec of separation. The number sounds abstract. Its consequence is not. When combined with the model's matter content, geometry, and dark energy, it produces a cosmic age of roughly 13.8 billion years. Then astronomers measure the expansion another way. Instead of looking back toward the infant universe, they build a distance ladder through the nearby cosmos. Cepheid variable stars provide calibrated distances to galaxies, while Type Ia supernovae extend those measurements much farther. Comparing distance with the recession of those galaxies reveals today's expansion rate. That method gives a value near 45 miles per second for every megaparsec. The difference is only a few miles per second on an immense cosmic scale. Yet that small gap changes the story of the universe itself. The two approaches disagree by roughly 9%, far beyond their quoted uncertainties. This is the Hubble tension. For years, researchers searched for hidden measurement errors. Could dust make distant stars appear dimmer? Could crowded stellar fields distort their brightness? Could the supernova calibration be subtly wrong? The James Webb Space Telescope has provided an important test. Its infrared observations of Cepheid variables have supported the earlier measurements from the Hubble Space Telescope, making a simple observational mistake increasingly difficult to maintain. The tension therefore reaches deeper than one instrument or one calibration technique. The early universe method and the nearby universe method may be describing a reality that our current cosmological model cannot connect perfectly. That matters for Methuselah because the Hubble constant helps determine the cosmic timeline. A lower expansion rate generally permits more time for the universe to reach its present state. If the true value were sufficiently lower, the universe could be older, easing the conflict with an exceptionally ancient star. A higher value pushes in the opposite direction. You can see why Methuselah has become interesting beyond stellar astronomy. Its age estimate comes from the physics of one star, while the Hubble constant comes from observations spanning the largest structures we can see. They are independent routes toward the same question: how much time has actually passed? Some researchers have explored whether ancient stars could provide an additional constraint on cosmic expansion. Methuselah cannot determine the Hubble constant by itself, but its age places a boundary on which cosmological histories remain plausible. The tension is therefore more than two competing numbers. It is a disagreement between two ways of reading cosmic time, with an ancient star sitting directly between them. Distance is where a star's apparent brightness becomes a physical measurement. Without it, we cannot know how much light Methuselah actually produces, and without that luminosity, its evolutionary state remains uncertain. Imagine moving the star farther away while keeping everything else unchanged. Its observed light would remain the same, but its true luminosity would have to be greater. A brighter intrinsic star occupies a different position in stellar models, changing the age calculated from its structure. Move it closer, and the opposite happens. That is why astronomers rely on parallax, a geometric method that needs no assumptions about how bright a star should be. As Earth travels around the Sun, a nearby star appears to shift slightly against much more distant background stars. The effect is tiny, but its geometry is simple. Earth's orbital path provides a baseline of roughly 186 million miles. From opposite sides of that path, Methuselah appears from minutely different directions. We can measure that displacement and use the angles to determine its distance directly. The shift is measured in arcseconds, an angular unit far smaller than a degree. Methuselah's parallax is only about 16.9 thousandths of an arcsecond. That is an extraordinary measurement. Howard Bond's observations with the Hubble Space Telescope's fine guidance sensors reduced the uncertainty dramatically. Across 11 separate observing periods, the instruments tracked Methuselah's position relative to background stars with a precision approaching 2/10 of a milliarcsecond. For a measurement involving a star nearly 200 light years away, that precision is remarkable. Yet the significance goes beyond the number itself. If the distance had been substantially wrong, the stellar age could have shifted with it. It did not. The European Space Agency's Gaia spacecraft later provided an independent measurement using a completely different observing system. Gaia was designed to map stellar positions and motions across the Milky Way, measuring parallaxes for enormous numbers of stars rather than concentrating on a small selection of targets. Methuselah's Gaia measurement remained consistent with the earlier distance determination. Two generations of astronomical instruments, separated by different technologies and observing strategies, converged on essentially the same location. That agreement removes one of the simplest explanations for the age problem. We cannot easily place the star somewhere else and make its evolutionary history younger. There is also a deeper consequence. Parallax measures geometry rather than stellar theory. The measurement does not depend on knowing how much iron Methuselah contains, how quickly its core burns, or how much helium lies inside it. You can therefore separate two questions that are often blended together. Where is the star, and how old is it? For Methuselah, the first question has become remarkably well constrained. The remaining uncertainty lies elsewhere, inside the physics used to interpret what that precisely measured star is doing. The distance may be firmly measured, yet the age remains flexible. That is because a stellar age is ultimately produced by a model, and models depend on details we cannot observe directly. Three variables matter, especially for Methuselah: the amount of helium inside the star, the balance between oxygen and iron, and the rate at which nuclear reactions consume hydrogen in its core. Helium presents a particular difficulty. It is abundant throughout the universe, but Methuselah's relatively cool atmosphere does not provide strong helium signatures that astronomers can measure reliably. We therefore infer its helium content from the conditions established by Big Bang nucleosynthesis, the early process that produced most of the universe's hydrogen and helium. A small change in that assumption can reshape the stellar clock. If Methuselah contains slightly more helium than the model expects, its interior evolves more rapidly. Hydrogen fuel is consumed at a different rate, changing the point where the star should appear along its evolutionary path. Oxygen introduces another complication. Inside a star, energy must travel outward from the hot interior. Elements influence how easily that energy moves through the stellar material, a property known as opacity. Oxygen is especially important because its abundance relative to iron affects the calculated structure and evolution of an ancient metal-poor star. Even modest changes in the assumed oxygen abundance can shift the predicted age by hundreds of millions of years. That is enormous when the entire disagreement with cosmology occupies a similar timescale. Then there is nuclear physics itself. The rate of fusion inside Methuselah depends on reaction probabilities calculated from laboratory measurements and theoretical models. These values are remarkably well understood, yet stellar evolution magnifies small differences over billions of years. A tiny change in the rate of energy production can alter how quickly the star moves through successive stages. We therefore have several layers of uncertainty interacting at once. The observed light is measured, the chemical composition is estimated, the interior structure is modeled, and the resulting evolution is compared against theoretical stellar tracks. The famous 14.46 billion year estimate represents the center of that calculation. It is not a declaration that Methuselah must have been born at precisely that moment. Instead, astronomers calculate a range of possible ages, weighted according to how well different models match the observations. Some combinations of assumptions produce younger results, others produce older ones. That distinction becomes crucial near the cosmic age boundary. When a star's estimated age sits close to 13.8 billion years, uncertainties that would be insignificant for a younger star become decisive. You can see the problem in the structure of the calculation itself. The distance is constrained by geometry, but the age depends on hidden properties inside the star. Those properties cannot simply be measured one by one and read from an instrument. They must be inferred through physics. Methuselah's paradox, therefore, survives inside that final layer, where observation ends and interpretation begins. The first stars left behind no surviving photographs, no preserved surfaces, and no direct record of their lives. Their existence is reconstructed from the material they scattered into space long after those first stellar furnaces disappeared. They are known as population 3 stars, the earliest generation to emerge from the primordial universe. Their birth marked a profound change. Before them, space contained mostly hydrogen and helium, with only traces of a few lighter elements created during the universe's first minutes. Then gravity gathered that gas into dense clouds. The earliest stars probably began appearing between 100 and 400 million years after the beginning of cosmic history. Their formation ended the cosmic dark ages, when the universe contained no stars bright enough to illuminate the surrounding gas. These first stars were unlike most stars we see today. Without generations of previous stars enriching their birth clouds, they contained almost none of the heavier elements that influence modern stellar formation. That lack of metals allowed their gas clouds to cool differently, and some models suggest the resulting stars became enormous. Individual population. Three stars may have reached hundreds of times the Sun's mass, with certain theoretical models allowing even greater masses. Their lives were correspondingly brief. A massive star consumes its nuclear fuel at an extraordinary rate. After only a few million years, some of these early giants would have exhausted the reactions supporting their cores and collapsed under their own gravity. Then came the explosions. Some ended through core collapse supernovae. Others may have experienced pair instability supernovae, a rare process capable of completely disrupting a massive star and dispersing its newly forged elements into surrounding space. Oxygen, carbon, and iron were among the materials released by these early deaths. For the first time, clouds of hydrogen and helium became contaminated with elements produced inside stars. That changed what could happen next. Gas carrying those new elements could cool more efficiently, collapse into later generations of stars, and preserve chemical traces of the stellar explosions that came before them. Methuselah belongs to this later population. Its atmosphere contains too little heavy material to represent a star born from heavily enriched gas. Yet it contains enough of those elements to show that its birth cloud had already encountered stellar debris. That makes its existence especially valuable. Population. Three stars themselves have never been confirmed through direct observation. They formed so early, lived so briefly, and existed at such immense distances that their individual light has been extraordinarily difficult to isolate. We instead search for their descendants. Stars like Methuselah preserve fragments of that vanished generation in their chemical composition. Each unusual abundance ratio offers another clue about the kinds of stars that enriched the gas before them. In that sense, Methuselah is more than an ancient survivor. It is a second generation witness carrying evidence from stars that disappeared billions of years before the Milky Way reached its present form. The original giants are gone, their elements remain, and inside Methuselah, we can still read traces of what those first stars left behind. The universe carries its own timestamp, written across the oldest light we can observe. That light comes from a much earlier moment, when the cosmos first became transparent enough for radiation to travel freely. We call this relic the cosmic microwave background. It is the thermal afterglow of the early universe, stretched by cosmic expansion until its original light arrives mainly at microwave wavelengths. Wherever you look, its faint radiation surrounds you. Its temperature is about minus 455 degrees Fahrenheit. The variations are extraordinarily small. Across the sky, neighboring regions differ by only tiny fractions of a degree. Those differences matter. They are ancient density variations, preserved from a time when matter and radiation were still closely coupled. Some began as quantum fluctuations in the infant universe, later amplified as gravity shaped the distribution of matter. When radiation finally separated from ordinary matter, those fluctuations became imprinted in the background light. Their pattern contains information about the contents and geometry of the universe, along with the conditions governing its expansion. Physicists measure the characteristic sizes of these features, compare their relative strengths, and use those measurements to test models of the universe. The European Space Agency's Planck satellite carried out the most detailed full-sky measurement of this radiation. Operating between 2009 and 2013, it mapped the background across the entire celestial sphere with remarkable precision. From that dataset, cosmologists derived several fundamental properties. They estimated ordinary matter, dark matter, dark energy, the expansion rate, and the age of the universe. Those measurements lead to an age of roughly 13.8 billion years. The precision is extraordinary. One major analysis placed the uncertainty at only about 21 million years, a remarkably narrow interval for a quantity describing the entire observable universe. That matters when we compare the result with Methuselah. A star carries uncertainties in its composition, internal structure, and evolutionary history. The cosmic microwave background is constrained through a different chain of evidence, built from the large-scale behavior of the universe itself. So we are comparing two clocks made from different physical systems. One is written in the life of a star. The other is written across the sky. For decades, cosmological observations and stellar evolution have agreed remarkably well. Yet Methuselah places unusual pressure on that agreement because its central age estimate reaches beyond the interval allowed by the cosmic clock. The discrepancy does not come from a vague impression that the star seems ancient. It emerges when measured stellar properties are compared with a cosmological age derived from an entirely different observation. That distinction is crucial. If the cosmic background has been interpreted correctly, Methuselah's central estimate must yield to uncertainties within stellar physics. If the stellar model is sound, the tension becomes harder to dismiss. The background radiation therefore gives us an independent reference point, built from the earliest light in the universe, against which Methuselah's calculated history can be tested. The age of the universe is partly a story about motion. Every galaxy carries evidence of cosmic expansion, and the pattern of that expansion changes across time. Early on, gravity dominated. Matter was packed more densely then, so its mutual attraction slowed the expansion of space. For billions of years, that slowing shaped the universe's growth, gradually changing how quickly distant galaxies separated. Then, roughly 5 billion years ago, the behavior changed. The expansion began accelerating. We call the unknown cause dark energy. The name sounds definitive, yet it describes a mystery rather than a substance we understand. We have not isolated dark energy in a laboratory, and no experiment has revealed what physical entity produces its effects. It appears to account for roughly 68% of the universe's total energy content. That makes it the dominant component of the cosmos, even though we cannot directly identify what it is. The simplest explanation is the cosmological constant, a fixed energy density associated with space itself. Albert Einstein introduced a related term into his equations of general relativity, later rejecting it after the expansion of the universe became known. Today, the cosmological constant remains the standard explanation for accelerated expansion. But standard does not mean certain. If dark energy has remained constant throughout cosmic history, then the expansion history used by modern cosmology follows one particular path. The age of the universe emerges from that path. Change the behavior of dark energy, and the path changes. That difference can accumulate over billions of years. A slightly different expansion rate in the distant past changes how long the universe required to reach its present state. You can think of the age calculation as a history reconstructed from motion. We observe where the universe is now, then use physical models to trace its expansion backward through time. If those models describe dark energy incorrectly, the reconstructed history also shifts. This possibility has gained attention from the Dark Energy Spectroscopic Instrument, which studies the distribution of galaxies across enormous cosmic volumes. Results released in 2024 found intriguing hints that dark energy may evolve rather than remain perfectly constant. The evidence is not yet decisive. Alternative analyses and additional observations are still being examined. Still, the possibility matters for Methuselah. Suppose dark energy behaved differently during the universe's earlier eras. The expansion could have followed a slower trajectory for longer, allowing more time to pass before reaching the present cosmic state. That would increase the inferred age of the universe. Even a modest change could matter when the difference is measured in hundreds of millions of years. Methuselah therefore sits within a larger question about whether our cosmic timeline captures every stage of expansion correctly. The star does not need to break cosmology by itself. It only needs to expose a place where the timeline remains uncertain. Helium sits at the center of a strange problem. We can detect many elements in Methuselah's atmosphere, yet one of the most important ingredients remains hidden from direct measurement. Helium is the second most abundant element in the universe. Roughly 1/4 of ordinary matter by mass is helium, much of it produced during the first minutes after the Big Bang. Methuselah formed with very little material, heavier than helium. That makes its helium content especially important, because there are few other clues available from its atmosphere. In a star this cool, helium leaves almost no useful absorption lines. The atoms simply do not reveal their abundance clearly through the spectrum we observe. So astronomers must infer it. That inference begins with Big Bang nucleosynthesis, the theory describing how the earliest universe produced its lightest elements. According to the standard picture, the primordial helium fraction is about 24.5% by mass. It sounds precise, yet the difference between reasonable assumptions can become enormous inside a stellar model. Increase the assumed helium fraction by 2 percentage points, and the star's internal evolution changes. More helium alters the balance of hydrogen available for nuclear fusion, affecting how the core processes its fuel over immense spans of time. The result is subtle at first. The model makes the star evolve faster. When astronomers compare that faster evolutionary path with Methuselah's observed temperature and brightness, the calculated age becomes younger. A relatively small adjustment in helium abundance can therefore shift the inferred age by hundreds of millions of years. For Methuselah, one study found that increasing the assumed helium fraction could lower the age estimate by roughly 700 million years. That shift alone approaches the scale required to bring the stellar calculation much closer to the accepted age of the universe. But the missing measurement remains. We cannot simply look at Methuselah and determine its helium content directly. The spectrum does not provide a reliable measurement, leaving the model dependent on assumptions about primordial chemistry. That creates a delicate chain of reasoning. We estimate the universe's original helium abundance. We use that estimate inside a stellar evolution model. The model predicts how the star changes with time, and those predictions become part of its calculated age. Each link can be scientifically reasonable, while the final result still carries uncertainty. The deeper issue reaches beyond one ancient star. Big Bang nucleosynthesis has been tested against several independent observations, including measurements of hydrogen and helium in extremely primitive environments. Those observations broadly support the theory. Still, small differences matter when the clock is measured in billions of years. Some researchers have explored whether the primordial helium abundance could differ slightly from the standard value. Such proposals remain debated, because changing the helium fraction must also remain consistent with other cosmological evidence. Methuselah therefore becomes an unusual test of two areas of physics at once. Its age depends partly on how accurately we understand the conditions that existed before the first stars were born. The oldest star in our neighborhood carries a hidden variable. We cannot see it directly, yet its assumed value can move the cosmic clock by hundreds of millions of years. Ancient stars rarely exist alone in the story of a galaxy. Across the Milky Way, thousands of stellar communities preserve evidence from its earliest eras, gathered into enormous spherical systems called globular clusters. A globular cluster is a dense gathering of stars, bound together by gravity. Some contain hundreds of thousands of stars, while the largest hold millions, with their members sharing similar birth conditions and broadly similar ages. That shared history gives astronomers something Methuselah cannot provide by itself, a population to compare against. The oldest globular clusters are estimated to be roughly 12.5 to 13.5 billion years old. Their ages come from stellar evolution models, using the positions of their stars on the Hertzsprung-Russell diagram and the changes expected as stars consume their nuclear fuel. These clusters, therefore, serve as natural laboratories for ancient stellar evolution. When many stars formed from the same cloud, differences between them become easier to interpret because their chemical starting conditions and ages can be compared across an entire population. One of the most remarkable examples is Omega Centauri, the largest globular cluster associated with the Milky Way. It contains roughly 10 million stars and has an unusually complex chemical history, suggesting that it may be the surviving core of a much larger system that was absorbed by our galaxy. Some of its stars are extremely poor in heavy elements, placing them among the oldest stellar populations we know. Methuselah, however, occupies a different place. It is a field star, meaning it travels through the galactic halo without remaining gravitationally bound to a globular cluster. We see it as an individual ancient traveler rather than one member of a dense stellar community. That raises an intriguing possibility. Methuselah could once have belonged to a cluster and been expelled through gravitational encounters with other stars. Alternatively, it may have formed independently within the early halo before the Milky Way had developed the structure we recognize today. Either possibility would connect Methuselah to the same ancient population represented by globular clusters, but the ages create an important distinction. The oldest known clusters reach roughly 13.5 billion years. Methuselah's central age estimate extends almost a billion years beyond that boundary. That difference matters because globular clusters are not isolated curiosities. Their existence demonstrates that large populations of stars were already forming remarkably early in cosmic history. If Methuselah truly belongs near the beginning of that era, its age would place it beyond the oldest established stellar communities. You would then have a single field star, apparently predating populations that already formed astonishingly close to the universe's beginning. The comparison gives astronomers another constraint. Ancient clusters establish one population-based timeline, while Methuselah provides an individual measurement from outside those systems. If both describe the same early universe, their clocks should broadly agree. The fact that they approach the cosmic limit from different directions makes Methuselah's remaining uncertainty even more important. Methuselah has entered a stage where the balance inside it is changing. Its central supply of hydrogen is nearly exhausted, and the star has begun leaving the long main sequence behind. We can think of this as a rearrangement of the furnace at its center. Hydrogen fusion once dominated the core, supporting the star against gravity and maintaining its familiar structure. Now, the core contains increasingly more helium, while hydrogen burning shifts into a surrounding shell. That change matters enormously. Shell burning releases energy through a larger region, pushing the outer layers outward as the helium core contracts and heats. The star becomes larger, brighter, and cooler at its surface. You can already place Methuselah on that path. Its surface temperature is roughly 10,000 degrees Fahrenheit, close to the temperature of the sun's visible surface. As the star expands, that temperature will fall, even while its total energy output increases. Eventually, Methuselah should become a red giant. Its outer atmosphere could expand to many times its present size, reaching dimensions that would transform the star's appearance completely. Inside, however, another transition will be taking shape. The contracting helium core will eventually become hot enough for helium fusion to begin. That process converts helium into heavier elements, primarily carbon and oxygen, through a chain of nuclear reactions that briefly gives the aging star another source of energy. For a star as low in mass as Methuselah, this stage cannot continue indefinitely. Once its usable nuclear fuel is exhausted, gravity will compress the remaining core until ordinary pressure from the matter itself can resist further collapse. The outer layers will then drift away into space. They may form a planetary nebula, a glowing shell of expelled gas surrounding the exposed stellar core. Despite the name, such a nebula has nothing to do with planets. What remains will be a white dwarf. Its mass will be packed into an object roughly comparable in size to Earth, with matter compressed to extraordinary densities. The core will contain mostly carbon and oxygen, remnants of the nuclear reactions that powered the star through its later stages. There will be no new fusion to sustain it. The white dwarf will simply radiate its stored heat into space, growing colder over immense stretches of time. You can follow that future backward and see why Methuselah is such a useful clock. Every stage of its present structure records the amount of nuclear fuel already consumed, the changing pressure within its interior, and the physics governing its evolution. Its eventual fate is therefore part of the same calculation that gives us its age. Methuselah will not explode as a supernova. It is too small for that ending. Instead, its transformation will unfold through expansion, shedding, contraction, and cooling, leaving behind a stellar remnant that may persist long after the Milky Way has changed beyond recognition. In astronomy, a measurement can become famous simply by refusing to disappear. Howard Bond's 2013 study did exactly that, placing Methuselah at the center of a problem that had already been hiding inside stellar age estimates. Bond and his collaborators observed the star during 11 separate epochs with the Hubble Space Telescope's fine guidance sensors. Each observing period added another piece to the parallax measurement, allowing the apparent motion of Methuselah to be tracked against much more distant background stars. The resulting distance was about 190 light-years, with an uncertainty of roughly half a light-year. That precision mattered because distance enters the stellar age calculation at a fundamental level. Once the distance was established, astronomers could determine the star's intrinsic brightness more accurately, then compare its properties with detailed models of stellar evolution. The result was a central age estimate of 14.46 billion years. The number was deeply uncomfortable. The estimated age of the universe was smaller, leaving a discrepancy that could not be dismissed as a simple measuring mistake. Bond's paper treated that tension directly, examining several possible changes in the underlying physics and stellar assumptions. One possibility involved helium. A different primordial helium abundance would alter how rapidly a star consumes hydrogen during its life, shifting the calculated age. Another involved the oxygen to iron ratio, which affects the opacity of stellar material and therefore the movement of energy through the star. A third possibility reached beyond the star itself, involving the value of the Hubble constant used to describe cosmic expansion. Bond did something important by placing those possibilities beside the observation. The paper did not select an easy answer. Instead, it showed where the calculation could bend and how much each change would need to accomplish. Its conclusion used unusually careful language, describing the stellar age as uncomfortably close to, and perhaps marginally inconsistent with, the age of the universe. For you, the meaning is simpler. Two carefully constructed clocks were giving different readings. The study appeared in the Astrophysical Journal Letters, and its influence spread across several fields. Stellar physicists revisited evolutionary models. Cosmologists examined expansion measurements. Researchers studying the early universe reconsidered the assumptions connecting primordial chemistry with ancient stars. Yet the years that followed did not erase Methuselah's problem. Better observations refined the distance, while improved models narrowed some uncertainties and exposed others. The central age estimate remained stubbornly high. That persistence is what gave the star its unusual scientific role. Methuselah became more than an old field star with an intriguing history. It became a test of whether several independent descriptions of the universe can occupy the same timeline. A discrepancy can be useful when it survives better data. It tells us exactly where our understanding still has room to change. The European Space Agency's Gaia satellite changed the Methuselah question by placing one star inside a much larger census. Launched in December 2013, Gaia began full science operations the following year, with a mission built around an extraordinary idea: measure positions, distances, and motions for more than 1 billion stars across the Milky Way. Its method is especially valuable here. Gaia measures parallax across an enormous population, rather than concentrating on a small group of carefully selected targets. Each star becomes another point in a three-dimensional map, allowing astronomers to trace how stellar populations are distributed and how they move through the galaxy. For Methuselah, the result mattered immediately. Gaia independently measured its parallax and found a distance consistent with Howard Bond's earlier determination within the uncertainties of both measurements. The agreement removed one of the simplest ways to explain the age problem. A major change in distance was no longer an easy escape. But Gaia's deeper contribution comes from the stars surrounding the case. Among the vast catalog are thousands of metal-poor stars moving through the galactic halo, carrying chemical patterns that resemble those found in Methuselah. Their distances and motions allow researchers to study these ancient populations statistically, rather than relying on one remarkable object. When many stars share similar chemical histories and evolutionary properties, their collective ages become a more powerful test. Analyses of these populations place many such stars across a broad range, extending from roughly 13 billion years to 14.5 billion years. Methuselah, therefore, begins to look less like an isolated anomaly and more like an especially precise member of an ancient stellar population. Gaia Data Release 3, published in 2022, expanded this picture dramatically. It provided measurements for an immense stellar catalog, including age estimates derived by combining Gaia observations with models of stellar evolution. Those ages are model-dependent, so they do not provide independent clocks in the strictest sense. Still, the pattern matters. Some of the oldest stars in these datasets approach the accepted age of the universe, while others can appear to cross it, depending on the models and uncertainties applied. The boundary becomes less like a sharp line and more like a region where several measurements overlap. For you, this changes the scale of the mystery. We are no longer comparing one ancient star against one cosmological number. We are comparing an entire population of stellar relics with the timeline constructed from cosmology. Gaia cannot decide which framework is wrong. Its strength lies elsewhere. By measuring so many stars with the same underlying method, it shows whether Methuselah's strange age belongs to a broader pattern. And that pattern reaches far beyond one star. The oldest halo populations keep pushing stellar evolution toward the earliest chapters of cosmic history, where even small changes in our assumptions can shift the apparent boundary between what the universe allows and what our models currently predict. One chemical ratio sits unusually close to the heart of Methuselah's age problem. The oxygen to iron ratio can reveal how energy moves through the star, making it one of the most important details in the entire calculation. Inside a star, radiation must travel outward from the nuclear furnace. The ease with which that energy moves depends partly on opacity, the tendency of stellar material to block or scatter radiation. Higher opacity keeps energy moving outward more slowly, changing the star's internal balance and extending the time required to consume its available fuel. That relationship gives oxygen an unusual influence. Methuselah contains very little iron compared with stars like the Sun, while oxygen remains comparatively abundant. Measuring that imbalance helps astronomers choose the stellar model that best matches the star's actual chemistry. Yet the measurements have never settled on one answer. Israelian and colleagues found an oxygen to iron enhancement of approximately 6 times the solar ratio. Another analysis by Bosgaard and colleagues produced a substantially lower value. The difference may look modest when written as a chemical abundance, but stellar models respond strongly to it. A shift of roughly 1/4 in the logarithmic oxygen to iron measurement can alter Methuselah's calculated age by hundreds of millions of years. In a problem already separated by less than 1 billion years, that is enormous. Consider what happens when the lower oxygen abundance is used. The resulting stellar model produces a younger Methuselah, bringing the central estimate down to roughly 13.96 billion years. Suddenly, the distance between the star and the accepted cosmic age becomes much smaller. That does not make the disagreement disappear automatically. The chemistry itself remains difficult to determine because astronomers do not measure oxygen abundance with a simple chemical test. Instead, they examine specific absorption features in the star's spectrum and compare those patterns with detailed models of its atmosphere. Different spectral lines can respond differently to temperature and pressure. Atmospheric models also make assumptions about convection, the movement of hot and cooler material through the star's outer layers. Even subtle differences in those assumptions can shift the inferred oxygen abundance. For you, this means the paradox can hinge on something remarkably small. A trace difference in the composition of an ancient star can propagate through an entire chain of stellar calculations, eventually changing an age by hundreds of millions of years. The oxygen question has therefore remained active for decades. Multiple teams have examined Methuselah with different instruments, methods, spectral features, and atmospheric assumptions, yet their results have not converged on one definitive ratio. We are left with a peculiar situation. The star's distance is tightly constrained, its motion is well measured, and its broader population is increasingly understood. But one chemical proportion buried inside its atmosphere still has enough influence to reshape the timeline. After roughly 25 years of investigation, the oxygen measurement remains unsettled, and that single unresolved ratio continues to occupy a surprisingly large space inside the age of one of the oldest stars we know. A star can carry a hidden history in the way it moves through space. For Methuselah, that possibility raises a simple question. Could another star once have changed what we think we are seeing today? Binary systems are common throughout the Milky Way. Two stars can remain gravitationally bound while orbiting a shared center of mass, sometimes separated by enormous distances. In closer systems, their evolution can become intertwined. As one star ages, it may expand enough for gravity to pull material toward its companion. That process is called mass transfer. Gas can flow from one stellar surface to another, gradually changing the masses and chemical histories of both stars. If Methuselah experienced such an exchange, its present condition could conceal part of its original story. A star that gains material becomes more massive than it was at birth, and stellar evolution models can interpret that increased mass as evidence of faster evolution. That matters directly for age calculations. Astronomers normally begin with the star's present properties, including its mass, brightness, temperature, and chemical composition. Those measurements are then compared against models describing how stars change over time. The calculation works best when today's mass remains reasonably close to the mass the star was born with. Mass transfer complicates that assumption. Methuselah could theoretically have gained material from a companion long ago, then continued evolving after that companion became difficult to detect. The original donor might have transformed into a faint remnant, or moved into an orbit so broad that its gravitational influence is subtle. We know these stellar exchanges occur. They help produce several unusual stellar systems and can ultimately contribute to some of the explosions we observe across the galaxy. For Methuselah, however, there is an important complication. Astronomers have searched for evidence of an orbiting partner by monitoring its radial velocity, the tiny changes in apparent motion caused by gravitational tugging from another object. A companion in a close orbit would produce a recognizable periodic pattern. Over repeated observations, the star would appear to move slightly toward and away from us as the two bodies traveled around their shared center of mass. No convincing pattern has emerged. That result places limits on the possibilities, but it does not close the door completely. A low-mass companion in a wide orbit could produce an extremely small signal, especially if its orbital period stretches across decades. Our observations, therefore, capture only part of the system's possible history. The absence of a detectable companion tells us that no obvious partner has revealed itself within the available data. It does not prove Methuselah was always alone. There is also a deeper reason this possibility matters. Stellar age calculations are built from assumptions that usually work remarkably well across enormous populations of stars. A hidden episode of mass exchange would introduce a different kind of uncertainty, one rooted in the star's personal history rather than the broader physics of stellar evolution. So the binary hypothesis remains on the table, although it is not considered the leading explanation. Methuselah has given astronomers no clear evidence of a companion yet, but the observations are still limited enough that a distant, faint partner cannot be completely excluded. A new kind of evidence is now gathering around Methuselah, arriving from an observatory built to study the earliest light in cosmic history. The James Webb Space Telescope gives astronomers something older instruments could not easily provide: exceptionally sensitive infrared spectroscopy. Its enormous primary mirror spans 21 feet 4 inches, assembled from 18 gold-coated beryllium segments. From its position beyond Earth's atmosphere, Webb can separate faint wavelengths with remarkable precision, allowing us to examine the chemical fingerprints embedded in ancient starlight. For Methuselah, that matters most where its age calculation remains vulnerable. Oxygen is one of the crucial variables. A refined measurement of the star's oxygen to iron ratio could change the stellar models used to estimate how long Methuselah has been evolving. Webb's near infrared spectrograph, an instrument designed to spread infrared light into a detailed spectrum, can measure subtle absorption features that reveal the abundances of different elements. Those features are faint in a metal poor star like Methuselah, where the chemical signals are already sparse. A better spectrum could therefore do more than improve a number. It could tell us whether earlier measurements were biased by the way stellar atmospheres were modeled, especially when scientists account for temperature, convection, and the formation of spectral lines. The same observations could examine carbon and other elements that influence stellar evolution. When several abundances are measured together, astronomers can test whether the assumptions inside their models remain consistent instead of adjusting one variable in isolation. There is another possibility hidden in the infrared. A companion object could be difficult to recognize through ordinary observations if it contributes little visible light, yet a faint excess of infrared emission might reveal additional material or a cool neighboring body. That evidence would not automatically solve the age problem. It would, however, change the physical picture from which the age is calculated. Webb also places Methuselah inside a much larger investigation. Astronomers are using the observatory to study metal-poor stars across the Milky Way and nearby dwarf galaxies, comparing their chemical compositions and evolutionary histories. Those observations give us something especially valuable, a population against which one unusual star can be tested. If many ancient stars display the same patterns, Methuselah becomes part of a broader stellar history rather than an isolated measurement. And if Webb finds that the oxygen abundance is higher than earlier work suggested, its calculated age could move downward. A hidden companion would introduce another correction. Either result could ease the tension, but a precise confirmation would carry a different implication. If Webb reproduces the existing composition with greater confidence, then the uncertainty surrounding Methuselah becomes harder to attribute to simple measurement error. The telescope cannot rewrite the age of the universe by itself. It can sharpen the stellar evidence until the remaining disagreement becomes much harder to dismiss. For a star whose age already presses against cosmological limits, that distinction matters. Methuselah becomes harder to dismiss when we stop looking at it alone. Across the Milky Way, other ancient stars carry their own evidence, and several approach the same uncomfortable boundary. Consider HD 140283, the star we know as Methuselah. Its age is unusually precise because its distance and physical properties have been measured so carefully. Yet another ancient star can arrive at a similar result through a very different path. HD 122563 is a red giant buried deep in the galactic halo. Its atmosphere contains remarkably little iron, indicating that it formed before later generations had enriched the galaxy with heavier elements. Stellar models place its age somewhere between 13 and 14 billion years. Then there is He 15230901. Discovered in 2007, this star offers an unusual clock. Instead of relying entirely on stellar evolution, astronomers can examine radioactive elements preserved in its atmosphere. Uranium and thorium decay at known rates. Their remaining abundances can therefore provide an independent estimate of when those elements were incorporated into the star. The result places HE1 5230901 at roughly 13.2 billion years old, with uncertainties extending toward 14 billion. That range matters. Another example is CS 310820001, an extremely metal poor halo star whose age has also been estimated through thorium decay. Its central estimate is around 12.5 billion years, but the uncertainty remains broad enough to approach the accepted cosmic boundary. Different clocks, similar problem. These stars are not scattered randomly through the galaxy. Many belong to the ancient stellar halo, the vast population surrounding the Milky Way's brighter central disk. Their chemical compositions preserve evidence from an era when the galaxy contained far fewer heavy elements. Some also move along unusual orbits, suggesting that parts of the halo were assembled from smaller systems that merged with the young Milky Way. Dwarf galaxies contributed some of this ancient material, carrying old stars into the growing galactic structure. When astronomers study these populations together, a pattern begins to emerge. A substantial number of ancient halo stars receive ages between 13 and 14.5 billion years. And the distribution does not simply end at 13.8 billion years. That detail changes the nature of the puzzle. If only Methuselah crossed the accepted boundary, an unusual measurement or overlooked stellar property would be the obvious suspect. But multiple ancient stars occupy the same territory. Their measurements come from different methods, different instruments, and different physical assumptions. Some depend heavily on stellar evolution models. Others use radioactive decay as a separate chronological tool. Yet their age estimates repeatedly gather near the same cosmic limit. For you, the important distinction is statistical. Methuselah may be the sharpest measurement, but it sits inside a much larger population of exceptionally old stars. That makes the tension harder to describe as one troublesome object. The question is becoming broader. Are we seeing a collection of unusual stars, or are these stars revealing something incomplete about the age we assign to the universe itself? A second clock can exist inside an ancient star built from atoms that slowly disappear. Unlike stellar evolution, this clock does not depend primarily on how a star changes its brightness, temperature, or structure over time. Some extremely old stars preserve radioactive elements forged before the stars themselves formed. Uranium and thorium decay at precisely measured rates, making their remaining abundance a kind of cosmic timestamp. The technique is called nucleochronometry or cosmochronology. It uses radioactive isotopes as clocks by comparing how much remains today with how much was originally produced. Uranium 238 has a half-life of 4.47 billion years. Thorium 232 lasts far longer, with a half-life of 14.05 billion years. Every passing interval changes their proportions in a predictable way. That predictability gives astronomers another route to stellar ages. The method becomes more powerful when radioactive elements are compared with stable elements such as europium. Scientists estimate the original production ratios from models of the rapid neutron capture process, a sequence of reactions capable of creating some of the heaviest elements known. Those elements can be scattered through space by violent stellar events. Later, they become part of new stars and remain locked within their atmospheres for billions of years. If we can measure the surviving radioactive material accurately enough, the decay itself becomes a record of elapsed time. For the ancient star HE 152309001, radioactive dating produced an age of about 13.2 billion years. That result was broadly consistent with ages obtained through stellar evolution models. The agreement matters because the two approaches rely on very different physics. Stellar evolution follows the internal behavior of a star. Radioactive dating follows the decay of individual atomic nuclei. When independent methods arrive near the same age, the possibility of a large systematic error becomes harder to maintain. Methuselah, however, cannot use this particular clock. Its atmosphere is extremely poor in heavy elements, leaving too little uranium and thorium for a reliable radioactive measurement. The same chemical scarcity that makes the star such an important relic also removes one of astronomy's most useful independent dating methods. So we have to look at other ancient stars instead. Their radioactive clocks provide a valuable test of the models used to interpret Methuselah. If evolution calculations repeatedly agree with radioactive ages across different stars, confidence in the underlying stellar physics grows. That does not automatically solve Methuselah's age. It changes how we weigh the uncertainty. Imagine measuring an old wooden object with one clock, then finding another clock inside a different object that gives nearly the same result. The second measurement does not date the first object directly, but it tells us something about whether the original clock can be trusted. The same principle applies here. Radioactive elements offer an independent check on stellar chronology, reaching across billions of years without depending on the star's present structure alone. For ancient halo stars, that agreement provides an important anchor, and for Methuselah, it means the age problem cannot simply be dismissed as a flaw in stellar evolution models. The models are being tested elsewhere against a completely different cosmic clock. Two numbers now divide modern cosmology, and the distance between them has become harder to ignore. One comes from the early universe, reconstructed from the cosmic microwave background, and the patterns preserved within its ancient radiation. The Planck collaboration measured an expansion rate corresponding to about 67.4 kilometers per second per megaparsec. That value leads to a universe roughly 13.8 billion years old. The other number emerges much closer to home. Astronomers measure Type Ia supernovae using Cepheid variable stars to establish their distances and calibrate the cosmic distance ladder. The resulting expansion rate is closer to 73 kilometers per second per megaparsec. That difference may sound small. Cosmologically, it is enormous. The higher value is closely associated with Adam Reus and the SH0ES collaboration at the Space Telescope Science Institute. Their observations repeatedly found a faster present-day expansion than the rate inferred from the early universe. Meanwhile, analyses based on the cosmic microwave background continue to describe a slower expansion history. Each side has refined its instruments, methods, calibrations, and statistical treatment. The disagreement has survived those improvements. In fact, it has become more significant. Physicists often describe such significance in terms of standard deviations. A discrepancy reaching 5 standard deviations corresponds to odds of less than 1 in 3.5 million that random statistical variation alone produced the result. That is why the Hubble tension has become more than a disagreement over decimals. It suggests that something within our picture of cosmic expansion may be incomplete. For Methuselah, the implications are unusually direct. If the higher expansion rate measured by the late universe approach is correct, the inferred cosmic age becomes younger. That leaves even less room for a star whose stellar models can approach 14.5 billion years. The paradox grows. But consider the opposite possibility. If the true expansion rate is somewhat lower than the early universe estimate, perhaps around 65 or 64 kilometers per second per megaparsec, the universe could reach an age of 14 billion years or more. Then Methuselah's apparent excess age would become much easier to accommodate. You can see why this distant star has become entangled with a much larger argument. Its age depends partly on stellar physics, while the universe's age depends partly on cosmological expansion. Those two clocks should agree. So far, they have not aligned perfectly. Methuselah cannot tell us which measurement is wrong. It simply provides another ancient record against which our calculations must be tested. The star has existed through an immense span of cosmic history, long before astronomers developed the instruments needed to measure that history. Now its structure is being compared with the expansion of the entire universe. And that creates an unusual situation. We are using one ancient star to question the age of everything around it. Three paths remain open around Methuselah, and each would change a different part of our understanding. The first leads inward, toward the physics of stars themselves. Perhaps the models are aging Methuselah too aggressively. A small error in helium abundance, oxygen abundance, or nuclear reaction rates could shift the calculated lifetime enough to bring the star beneath the universe's accepted age. That would be a profound result. Stellar evolution would need revision. Cosmology could remain intact. Our equations describing stars would have to become more precise, especially for ancient, metal-poor objects whose compositions differ greatly from the sunday. Even a modest systematic error can accumulate across billions of years when a model uses temperature, brightness, mass, and chemical abundance together. The second path leads outward. Perhaps the universe itself is older than current measurements indicate. A lower value for the Hubble constant could lengthen the inferred cosmic age, while an incomplete understanding of dark energy could alter the expansion history used to calculate it. The consequences would reach much farther. Our standard cosmological model could require modification. The framework, known as lambda cold dark matter, connects the expansion of space, the abundance of matter, and the behavior of dark energy into one coherent picture. Change one part, and others may need adjustment. Then there is a third possibility, less dramatic, but perhaps more realistic. Methuselah could turn out to be somewhat younger, while the universe could turn out to be somewhat older. Neither field would need to collapse. Instead, several small corrections could close the distance between the two clocks. A revised oxygen abundance, improved stellar atmosphere models, and a refined cosmic expansion rate might each move the estimates slightly. Together, those changes could be enough. You can think of this as a problem of overlapping uncertainties. Each measurement carries its own range of possible values, and the real answer may lie where those ranges finally meet. There is also a more radical possibility. Perhaps our observable universe does not represent everything that exists. Some speculative ideas allow for regions with different histories or conditions beyond the portion of the cosmos we can observe. There is no compelling evidence for such a scenario. Most physicists would place it far below the more ordinary explanations. That distinction matters. Science does not treat every imaginable answer equally. The conservative expectation is that several smaller corrections will eventually resolve the tension. Yet, an expectation remains different from a measurement. As long as Methuselah's central age remains above the strongest estimates for the universe's age, something remains unresolved. The disagreement could eventually disappear through better observations, improved stellar models, or a revised picture of cosmic expansion. Or it could expose a deeper weakness in one of our most successful theories. For now, we have an unusually precise question without an equally precise answer. One ancient star has forced stellar physics and cosmology to compare their clocks, and neither can completely dismiss what the other is showing. Tonight, The light from Methuselah reaches us after traveling across 190 light years of space. What arrives at your eyes began its journey long before modern astronomy existed. The photons entering a telescope tonight left the star around 1836. Charles Darwin had not yet published On the Origin of Species. The American Civil War remained decades away. Human history was moving through another century while this ancient star continued its own measured evolution. There is another clock inside that light. The hydrogen fueling Methuselah is primordial material created during the first few minutes after the Big Bang. That hydrogen has remained part of the cosmic story for almost the entire lifetime of the universe. Inside the star, some of those hydrogen nuclei eventually reach the conditions required for fusion. They combine through a sequence of nuclear reactions, producing helium and releasing energy in the process. That energy becomes part of the radiation moving outward. It takes time. Photons created deep within a star do not simply travel straight to its surface. They interact repeatedly with matter, transferring energy through the stellar interior before eventually escaping into space. Once they emerge, their journey becomes much simpler. They cross the darkness between stars. After roughly 190 years, some reach Earth. A few may strike a telescope mirror. Others may enter your eyes if you are observing under a suitable sky. For you, the experience lasts an instant. For the photon, the journey has crossed an enormous distance, and what reaches us carries information about conditions inside a star that began forming before Earth existed. Its spectrum records chemical fingerprints, temperature, motion, and other properties that astronomers can measure from across interstellar space. The light, therefore, becomes more than an image. It becomes evidence. When we look toward Methuselah, we are receiving a message from a much earlier chapter of cosmic history. The universe then contained far fewer heavy elements, because most of the elements familiar to us had not yet been produced in large quantities. There were no human observers waiting for that light. No Earth existed. No sun had formed. No planet in our solar system had begun its long history. Yet the material that eventually became Methuselah was already part of an evolving cosmos. Hydrogen from the early universe became fuel. Stars transformed portions of that material, and generations of stellar activity gradually enriched the galaxies that followed. Methuselah belongs to that ancient chain. Its light has crossed the same universe that later produced planets, oceans, civilizations, and you. Every year that passes here adds another year to the distance between the stars present and the light we receive. What you see tonight is therefore always a record of an earlier Methuselah. The star itself has already moved beyond that moment. We are seeing its history. And while that ancient light continues toward us, Methuselah remains far beyond human reach, following its own stellar evolution, indifferent to the civilizations studying the photons it sends across the galaxy. A catalog entry rarely carries a story of its own. HD 14028. 3 began as a number, assigned within the Henry Draper Catalog, a vast stellar survey built from the spectra of more than 225,000 stars. Its formal identity is precise. Its familiar name is something else entirely. Astronomers began calling the star Methuselah as its extraordinary age became increasingly difficult to ignore. The name comes from the book of Genesis, where Methuselah is described as the grandfather of Noah and the son of Enoch. According to the biblical account, he lived 969 years. That number became part of the name's meaning, Across generations, Methuselah came to represent extreme age, almost beyond ordinary human imagination. You can find the name in places far removed from astronomy. Methuselah trees, Methuselah wine bottles, and even longevity studies have borrowed it as shorthand for exceptional endurance. For this star, the comparison is almost absurdly small. Methuselah has existed for billions of years. The oldest known living organism is a bristlecone pine named Methuselah, growing in California's White Mountains. Its estimated age is around 4,855 years. The tree is ancient by every human measure. Against the star, it has barely begun. When that bristlecone pine was still a seedling, the star had already existed for roughly 14 billion years. Entire landscapes had changed repeatedly during the tree's lifetime, while Methuselah had already passed through almost incomprehensible stretches of stellar history. There is something revealing in that contrast. We tend to measure age through familiar objects. A person's lifetime gives us one scale. A civilization gives us another. Written history extends farther, and geological time pushes beyond anything our instincts easily grasp. Then astronomy introduces billions of years. A name becomes useful there. Methuselah gives our minds a handle for an object whose true history cannot be experienced directly. We can pronounce it, remember it, and return to it in conversation. The official catalog number remains essential to science. It identifies the star precisely among countless others, allowing observations from different instruments and different generations of astronomers to refer to the same object. But the informal name carries something different. It carries context. Every time we say Methuselah, we are connecting an ancient stellar object with one of humanity's oldest stories about longevity. The connection was never required by physics. No scientific instrument needed the biblical reference. Yet language often reaches places that equations cannot. A designation tells us which star we are studying. A name tells us why we keep returning to it. Methuselah does not know the story attached to its light. It does not know the tree sharing its name, or the ancient text that inspired it, or the people measuring its age from across space. Those meanings belong entirely to us. Perhaps that is why the name endured. Faced with an object older than our planet, our species, and nearly every structure we can see around us, we reached for the oldest symbol of age we already knew. And we gave that symbol to a star. Beyond the edge of what our telescopes can reveal, the universe does not simply end. Our view has a boundary, created by the finite age of light itself, and everything beyond it remains outside direct observation. The observable universe reaches roughly 46 billion light-years in every direction. That enormous distance describes the region whose ancient light has had enough time to reach us, even though the space itself has expanded while that light traveled. Past that horizon, we have no direct picture. We can still reason about what lies beyond. The same physical laws appear to govern distant galaxies, ancient stars, and the space around us, giving cosmologists a framework for considering regions we cannot observe directly. Ancient stars are especially valuable within that framework. Their atmospheres preserve chemical conditions from an era when the cosmos was still building its first generations of structure. Before stars filled galaxies with heavier elements, most ordinary matter consisted of hydrogen and helium, with only tiny traces of anything else. Methuselah belongs to that sparse chemical world. Its low abundance of heavier elements records an early cosmic environment when fewer generations of stars had lived and died. The star's orbit adds another piece of history because its path through the Milky Way can reveal clues about how our galaxy assembled from smaller systems. Its age carries an even deeper possibility. If we can determine that age precisely, we gain a timestamp for one of the earliest periods of stellar formation. That timestamp can be compared with models of cosmic expansion, galaxy formation, and the emergence of the first stars. So when you look at an ancient star, you are looking at more than an isolated object. You are sampling the conditions of the universe itself. There is an intimate connection between that distant history and your own body. Every element heavier than hydrogen in you was produced through cosmic processes that occurred after the earliest moments of creation. The iron in your blood came from earlier generations of stars and stellar explosions. Much of the oxygen you breathe was forged inside massive stars before being scattered into space. Hydrogen is different. Most of it is primordial, meaning it was created during the first minutes of the universe rather than forged inside later stars. The hydrogen bound into water, living tissue, and countless molecules around you carries an origin older than Earth itself. Methuselah contains a remarkable share of that ancient material. Its chemistry preserves a world that existed before planets, before Earth, and before life had any known place to begin. We cannot travel back to those first cosmic chapters. We cannot watch the earliest stars ignite directly. But ancient stars let us read traces of that era in the present. That makes Methuselah more than an old star. It is evidence from a universe we can only partially see, carrying information from a time when the architecture surrounding us was still taking shape. Science rarely advances in the places where every measurement agrees. The deeper changes often begin with a stubborn number that refuses to settle into the expected pattern. Astronomy has encountered this before. Strange stellar motions eventually revealed evidence for dark matter. Distant redshifts helped establish that the universe itself is expanding. Then observations of distant supernovae showed expansion changing over cosmic time, leading to the discovery of dark energy. Each discovery began with an uncomfortable mismatch. At first, an unexpected result can look like an ordinary mistake. Perhaps the instrument needs calibration. Perhaps the sample is too small. Perhaps an assumption inside the model has introduced a subtle bias. Researchers test those possibilities. If the discrepancy survives, attention shifts towards systematic effects. Better instruments are brought in. Independent teams repeat the measurement. Different methods attack the same problem from separate directions. Methuselah has passed through that process for decades. Its distance has been refined. Its chemical composition has been measured repeatedly. Stellar models have been adjusted and challenged. Cosmological measurements have become more precise. Still, the tension remains. That persistence matters. A temporary anomaly can disappear when the data improve. A durable anomaly becomes something different, especially when independent measurements continue pointing toward the same uncomfortable region. You can see why scientists remain cautious. A single ancient star cannot overturn an entire framework built from thousands of observations. Yet, neither can a persistent contradiction be dismissed simply because the existing framework is successful elsewhere. The most interesting problems often live between those two positions. Methuselah occupies that boundary. Its estimated age depends on physics that has been tested across generations of stars. The universe's age comes from entirely different observations, including relic radiation from the early cosmos and measurements of expansion. Those methods do not share the same instruments or immediate assumptions. Their disagreement, therefore, reaches deeper than one faulty reading. Popular explanations sometimes make the problem sound simpler than it is. One side can be portrayed as having made a mistake, while the other appears completely secure. Real scientific investigation is more complicated. Researchers compare uncertainties, recalibrate instruments, examine stellar chemistry, refine nuclear reaction rates, and reconsider assumptions about cosmic expansion. Every improvement changes the shape of the disagreement. That is why a paradox surviving better measurements deserves attention. It becomes sharper. The possibility is subtle. Perhaps stellar evolution contains a small systematic error. Perhaps cosmology carries an overlooked assumption. Perhaps both descriptions are slightly incomplete, allowing their errors to meet somewhere between the current estimates. We do not need a dramatic revolution to learn something fundamental. A small correction in one part of physics can reveal a larger relationship that was previously hidden. Methuselah may eventually become an ordinary entry in a stellar catalog once its age is reconciled with everything else we know. Or the discrepancy may remain, pointing toward physics we have not yet understood. Either outcome would be valuable, because science depends on finding the places where evidence and theory disagree, then staying with the disagreement long enough to understand it. Methuselah has given us exactly that kind of problem, preserved for generations in the light of an ancient star. Before we ask what Methuselah tells us, consider what makes the question possible at all. You are part of the measurement. The star has existed for roughly 14 billion years. For nearly all of that span, no known observer was present to name it, measure it, or wonder about its age. Then, within a remarkably brief chapter of cosmic history, matter assembled into beings capable of asking questions about distant suns. Our bodies are built from atoms forged through ancient cosmic processes, yet those atoms became organized into eyes, minds, instruments, and institutions. A question as simple as how old is that star carries an extraordinary chain of human achievement. It requires language to describe the problem, mathematics to express it, physics to model stellar interiors, telescopes to gather faint light, and carefully calibrated instruments to turn that light into evidence. It also requires time. Researchers compare observations across years and decades. They challenge assumptions, publish measurements, examine disagreements, and return to the same object with better tools. Methuselah became part of that process without ever changing its purpose. The star simply burns. It does not know its catalog designation. It cannot recognize a telescope. Nothing within it responds to the arguments taking place on Earth about whether its age is compatible with the universe around it. Yet the paradox is real in another sense. It exists between observation and explanation. We measure something in the sky, then build a model capable of describing it. When those two align, the model earns confidence. When they diverge, we have a choice: discard the observation, revise the model, or investigate the space between them. That space is where science becomes especially revealing. Our theories are extraordinarily powerful. They predict the behavior of stars, galaxies, particles, and expanding space with astonishing precision. Still, every theory rests on assumptions, and every generation inherits descriptions that can eventually encounter evidence they cannot fully explain. Methuselah offers that kind of encounter. You do not need to imagine the star as a message deliberately sent across space. Its existence is enough. Its light reaches us, our instruments record it, and human minds construct meaning from those measurements. That chain is fragile, yet remarkably effective. A civilization can look at an ancient point of light and reconstruct pieces of its history. We can estimate its chemistry, trace its motion, compare its structure with physical models, and ask whether the surrounding universe is as old as the evidence suggests. Perhaps the answer will come from better measurements. Perhaps improved stellar physics will close the remaining gap. Perhaps cosmology itself will require refinement. Whatever happens, the uncertainty has value. The universe does not owe us an explanation that fits neatly inside our current understanding. We are the ones doing the fitting, testing each idea against what nature allows us to observe. And that may be the most human part of this story. We look outward, discover something that does not quite fit, and keep looking. Long after the argument over Methuselah's age has faded from scientific journals, the star will continue along its own physical path. Better stellar models may revise its history, or cosmology may change, but neither possibility alters the slow sequence written into its interior. In a few billion years, Methuselah will exhaust the hydrogen available for its present stage of fusion. Its core will contract while the outer layers expand, transforming the familiar subgiant into a red giant. The surface will become cooler, while the enlarged atmosphere reaches far beyond its current boundaries. For a time, the star will shine with greater luminosity. Then, its structure will change again. As the core contracts and heats, helium will become the dominant fuel of its central reactions. Eventually, the outer atmosphere will be shed into space, creating a planetary nebula, a glowing shell of gas illuminated by the exposed stellar core. The nebula will not last forever. Its material will spread outward and gradually merge with the surrounding interstellar medium. At the center, the remaining core will become a white dwarf, a dense stellar remnant, roughly comparable in size to Earth. That remnant will no longer generate energy through ordinary nuclear fusion. Instead, it will release the heat stored within its compressed matter, fading over immense spans of time. You can imagine the timescale only by leaving human history behind. The sun will eventually exhaust its own fuel, and Earth will cease to exist in its present form long before Methuselah's remnant approaches its final darkness. Even the galaxy around it will change. Stars will be born, age, and disappear. Galaxies will merge. New generations of planetary systems will appear and vanish, while the space between distant galaxies continues expanding. Far into that future, Methuselah's white dwarf would become progressively dimmer, passing through stages of cooling until its remaining heat is almost impossible to detect. A fully cooled black dwarf is a theoretical endpoint because the universe is not yet old enough for any such object to exist. The contrast is extraordinary. We spend years refining a stellar age by fractions of a billion years, while the star itself operates on timescales vastly beyond civilization. Our instruments measure its present state, our models reconstruct its past, and our questions give meaning to measurements that the star never needed to answer. Methuselah will eventually lose the brilliance that makes it visible tonight. Its final remnant will drift through the galactic halo as the cosmos continues changing around it. The paradox may be solved within our lifetimes. The star will not care. It came from an ancient universe, and its remains may persist long after our present understanding has been replaced. Tonight, we see only one brief chapter of that existence, a distant point of starlight that has already outlived almost everything that ever tried to measure it.